So a weakening condition is cut sparsifiers. So graph is just a set of terminals that approximately preserves the value of minimum cuts supporting those subset of terminals. For example, u, v minus u, and the cut function h, these are defined in the thesis of Ancur-Moitra, so I just review it. So the cut function of any set u, for example here, is just the sum of the capacities going across the cut. So this one, sum of this, and this, if you sum all of them, so it's the sum of all of the capacities going across the cut. So E is inside the set of edges crossing the cut u and v minus u. And the mean cut function is just the minimum of that. And so now, alternatively, you could use just the terminals. I mean, you could define hk of A, which is just the cut function on k terminals, which is the minimum of h of u. But u is just has some intersection with terminals. A set of pairs which cross the partition is called delta k of A. If H is a cut sparsifier and a terminal set K, if H is a graph on just a terminal set, and if the cut function H prime of H satisfies Hk of A is less that. So this is H is now a cut sparsifier because this is for H, this is for G. So we have we have preserved that and we have taken that into consideration. Another things that you need to know, definition, the quality of the cut sparsifier is just the maximum of H prime divided by HK. So they are very natural definitions, as you could expect. A measure of local connectivity is the minimum cut in G separating A and B, and this is the motivation for many researchers. And now I want to talk about flow sparsifiers. We talked about cut sparsifier, now we're talking about flow sparsifiers. Remember min cut max flow theorem. Your max flow cannot be greater than min cut. So it's a dual of that. And what I want to say is about flow sparsifiers. So maximum concurrent flow problem, which is the largest fraction of demand, can be simultaneously satisfied. Can we do it? If we can do it, then we have solved the LP concurrent flow. LP concurrent flow. It means that you maximize lambda such that the flow, sum of the flow is greater than lambda Fi. But here Fi is not flow. Do not forget that this is a demand. Flow is X. So, and you have to respect the constraint that it cannot go for any path which edge is inside that. You cannot go more than the capacity. The congestion is not be like that it goes more than the capacity. And the dual problem is just the minimum, the distance times the capacity. So you see how it is, the dual of this problem is just like the zero extension problem that I will describe again and solve it using CKR randomized rounding. And so we solve this subject to d of E is greater than d of Si and Ti. And the the induced semi-metric, and K is just D of SI and TI. Fi is greater than 1. This is the demand. And of course, the distance between Si and Ti should be greater than 0, and D of E should be greater than 0. So the maximum multi-commodity flow, as I said, is just bounded by minimum multi-cut. So you can think of it as a generalization of max flow mean cut theorem. So every path, at least one edge of E prime, which is a minimum cost subset of E. And that's why we define congestion of F to be 1 over lambda star. And so H is a flow sparsifier if we can say that congestion of is less than congestion of F in G. So H is always better. So flow sparsifier is a better flow network than the original networks. I mean, all demands that are routable in G can also be routable in G, in H. So the quality of flow sparsifier, as I said before, is just the maximum of this congestion of F divided by, because each solver of your zero extension problem, because it is a randomized solution. So each time for example, you use CKR once, you get one answer. You use CKR another time, you get another answer. So different solution, but each of them gives you a different quality. And so you might say, okay, I try CKR algorithm several times until I see a good quality. And then I cut off. I don't continue. I just stop the algorithm. I just stop using the algorithm again and again. And that's another approach. So flow sparsification is not easier than cut sparsification. Make flow sparsifiers from cut sparsifiers. And we need to know what is semi-metric relaxation. And so we call an optimization problem a fractional graph partitioning problem if it can be written as minimum of C and U, the cost of or capacity of U and V, D of the distance between U and V. You minimize it such that D is a semi-metric and F is a monotone increasing function. So this is a graph partitioning problem, and the goal is to separate pairs of terminals without stretching too many high capacity edges. And once again, we can say that the maximal concurrent flow is related to integral dual, which is a generalized sparse cut. I mean, here we minimize C of E, D of E, but such that RD of A and B is greater than 1. So we give demand vector R, K, choose 2. We give this to this maximal concurrent flow, but another problem is like given some pairs of terminals T from K choose 2, but we give it now to maximum multiflow, which is the maximum of R, A, and B. We want to find R. Now we want to find your demand, such that it is the integral to all of that is that it is multi-cut. Here it was we use it for generalized sparse cut. Now here we use it for multi-cut. So you see how all of them are just one problem. You are solving it from different perspective. Min cut, max flow, all of them are dual things. And Vazirani showed that max flow is less than mean multi-cut, and mean multi-cut by a factor of log k. So about vertex sparsifier, they are order of log k over log k quality vertex sparsifiers, both for approximating cuts and multi-commodity flows. So let's run a game. A game is that the extension player. So you see that the extension player plays an important role in all of this, all of the problems in graph theory. And then use this to construct a vertex sparsifier, H. And the quality player wants to delay this, because each time check quality. He's not satisfied with the game. He wants to say, oh, you're not good enough. So this game goes until we get some kind of equilibrium. And this zero extension game, which extension player plays, it was first invented by 1998 paper of Karzhanov. Very highly cited article, and the title is I forgot the title, but it is a generalization of minimum multi-way cut problem, and the goal is to find a map, or in some problems we say optimal location gamma from V to T, such that you want to minimize over all those optimal locations C of xy times mu of gamma x and gamma y. I will explain it in different formulation that is more widely known and repeated in different lectures of people in Simon's Institute, so that everybody can see it is a very general framework that you can solve many problems. Just like the correlation clustering problem, that we can solve all cut problems using just correlation clustering. You can formulate it such that it can, when you solve this, so it is reduced to correlation clustering problems in the language of hardness of approximation. So we can say that of course these are not proved, but we may say that the conjecture could be it is as hard as solving any formulation of correlation clustering. So to solve this zero extension problem, I will explain some work of the CKR algorithm, the popular CKR algorithm. This is Kalinsky, Karlov, and Rabani. And people like Satish Rao and Kunal Talwar improved that algorithm and they get better approximation using their article, and improved approximation algorithm for zero extension in 2003. So I think I should explain CKR algorithm later because it's a huge topic and one of the most interesting and exciting part of all of these randomized rounding examples. So the cut sparsifier is, zero extension. In 2009, there is an article by Ankur Moitra, the same author that wrote that thesis that I suggested you to read. The title is Approximation Algorithms for Multi-Commodity Type Problems with Guarantees Independent of the Graph Size. And so we can observe that contracting an edge cannot decrease the minimum cut separating A from K minus A. So you should observe that contracting an edge, of course, endpoints, assume that endpoints are not both terminals. Both of them are not terminals, because if you contract them, then you get rid of one of the terminals, and this is not what we want. So contracting an edge cannot decrease the value of min cut separating A from K minus A. And using this, we can say contract until, so you solve your zero extension problem, for example here, you solve it, you get that this is the cut is like this, and all of the vertices here are mapped to this, so we have rounded like this, and then you contract all of this. It means that instead of this, you get just two terminals here, and two terminals here, and you get the cut. So you contract to get the sparsifier. You contract until only remaining nodes are terminal. It's very nice because this is a cut sparsifier. And all of the proofs and theorems is just about this. You contract the solution of that zero extension problem, and then you get the cut spar. Of course, not like this, because you have to play that zero extension and quality game until you get it converges to a kind of Nash equilibrium, and after that you can contract until you get your cut sparsifier. So Karzanov, again in 1998, used zero extension to define a graph partitioning problem that generalizes minimum multi. So he generalizes minimum multi-way cut problem. It's 41 pages, this article, but each word is important again. Minimum zero extension of graph metrics. His article. Minimum zero extension of graph metrics. D is a semi-metric on terminals, and the goal is to assign each node in V a terminal in K. Because we are doing a rounding, and rounding means that we assign each node in V. So the minimum zero extension problem, which is highly important, is just is this. And F, when we say zero extension function, I mean F. because for a different round of this, the game of zero extension player plays with the equality player. In each round of the game,